All right, welcome back. So we're going to continue with our free response questions. I am bouncing around because some stuff has been cut, and some stuff is hard to talk through. So a lot of the stuff with free body diagrams I've been skipping and assigning for homework. So we've got 2014 question 2, and then we'll have questions 1 and 3 for homework. So objective is to determine the speed, normal force, tangential acceleration, free body diagram, and all relevant forces and net forces acting on a block that slides down a ramp before being forced into circular sideways motion by a guiding rail, which looks like this. So we've got our ramp and a guiding rail. This is a little bit hard to this is a little bit small. Can you still see? Okay. So we get the block of mass m starting from rest at the top of a frictionless ramp. It's a height h above the tabletop. It slides down the ramp, reaches a point P with speed VO. So that's at the end of the ramp, P. After point P, it slides on the tabletop, guided by a circular vertical wall with radius r, which is shown in this top view here. So slides down the ramp and then gets turned by this circular guiding rail while it's on the desk. The tabletop has negligible friction, and the coefficient of kinetic friction between the block and the circular wall is mu. For part A, they want us to derive an expression for the height of the ramp and express our answer in terms of the initial velocity, mass, and any fundamental constants. Right, we need a general form before we do that first. So what did you just do? Perfect. Did I just skip a slide? I did. Kinetic final is equal to potential energy. Initial. Okay, so that's 1/2, you said, oops, lost the pen. 1/2 mv squared. And that's v final is equal to mgh initial. Okay. And we are solving for h, so what's going to happen? Okay, so we're left with okay. Hold on. It says express your answer in terms of VO. Oh, okay. Our subscripts are different. So the initial velocity, they've said is the initial velocity at point P. So I'm going to subscript this VO just so that we match what they wanted us to express this in terms of. So that was here. Express our answer in terms of VO, and then VO is what the speed is at point P. Okay. Any questions, part A? And part B? A short time after passing point P, the block is in contact with the wall and moves with the speed of velocity v. Is the vertical component of the net force upward, downward, or 0? So again, this is while it's on the guiding rail. Okay, right 0. Why? Is there any acceleration vertically? Right. Okay, 0 as there is no vertical acceleration, I'll say. Our normal force is balancing with gravity, otherwise our object would be going through the table. Okay. Then for part 2, on the figure below, draw an arrow starting on the block to indicate the direction of the horizontal component of the net force when it's on this position here where the coordinate plane is. So what should I draw? We're just looking at the horizontal components. Because we've got a top-down view. Okay. We're going to draw the net force, but there is a normal force that's acting on it, and then what else? Okay, so you've got a normal force that's going to push the block like this. And then what else? Gravity is not going to show because this is just looking horizontally. So my normal force is pushing me left right now. Is the object accelerating or decelerating? Decelerating. What's causing it to decelerate? Friction. So my net force should be pointing in what direction? Perfect. So down and to the left. Okay. And we'll justify our answer. I'm going to write in yellow over here, so B2. So there. Okay, friction. Decelerating the block. And a normal force providing centripetal acceleration. Okay. Part C. We're going to derive an expression for the magnitude of the normal force exerted on the block by the circular wall as an expression of V. Okay. Can you think of any equation involving a normal force right now using our top-down view? Perfect. So my normal force is centripetal force. What's our centripetal force? mv squared over r. Perfect. That's a capital R for us. Our radius is constant and our mass is constant, so that means this should be okay, actually. So we're already in expression for V. Okay, that was easier than it looked. Part D. Derive an expression for the magnitude of the tangential acceleration of the block at the instant the block has attained a speed of V. Okay, so I've got negative force of friction, so that's acting in the opposite direction. Should be equal to ma, or net force. What's our formula for force of friction? Negative mu Fn is equal to ma. Okay, and that acceleration should be at a specific time. That's at the instant the block attained a speed of v. I'm going to subscript this t. Okay. Then we're going to substitute. So I need to be able to solve this for at the instant the time is v. But we already have a function for normal force from part C. So I can plug that in. So that's negative mu mv squared over r equals mat. Okay, and then solve for a. Okay, so that leaves us with negative mu v squared over r. Okay. Oh. I guess we didn't need that negative after all, since this is magnitude. I'm just going to take the absolute value. So my final answer will be AT equals the absolute value of negative mu v squared over r. We'll check the scoring guides afterwards. They probably didn't use absolute value at all. They probably just left that positive the whole time, but oh well. Then for E, I want to derive an expression for Vt. The speed of the block is a function of time after passing point P. Okay, I'm going to go back really quick. So we've got some stuff we can use. We need an equation for V at any time after we pass point P. Okay, any clue when we start? Which one? Right. AT is dv over dt. And we said that was equal to negative mu v squared over r. So now we've got a separable differential equation that we can integrate. What's going to happen when I integrate? Okay, the mu and the r are constants. So when I integrate, what's going to happen? Okay, wait, we've actually got bounds here. So let me go back. Because our bounds are going to be different. When we go to integrate this, we're integrating velocity from what to what and time from what to what. Velocity is from, okay, v sub 0 to, so initial velocity on the ramp until, okay, I'm just going to call it v, velocity right now. Okay, so that leaves us with negative 1 over v from v final to v right now is equal to negative mu over r t from 0 to t. Okay, so do upper bound minus lower bounds, and then we'll be good to go. Okay. Sure, plus 0. Okay, so I don't think we do, but we can leave it as v naught. It says we can express our answer in terms of v naught. So that's okay. We need to solve for v. Okay, I'm just going to multiply through by negative 1, I think. So 1 over v plus 1 over, oh, sorry, minus 1 over v naught is equal to mu t over r, solve for v. Okay, we will, let's get this into a common fraction first, and then we'll do we'll flip it. So therefore v is equal to, okay, that should work. Awesome. I'm going to pull up the scoring guides really quick because I kind of want to see what they did with part D. Yeah, because they had that magnitude thing here, magnitude of the tangential acceleration. Okay, they did solve it through with a negative sign, and just said it's not needed. So no penalty for having it or not having it. Okay, cool. Any questions on anything we did? All right, so the homework is going to be part 1 and 3 from those free response, which is already linked on WeChat. And I'm going to save our annotations in case you want this for your notes. Okay. So when we meet again on Wednesday, I'm going to try to assign some stuff through the AP classroom. I know I've been pulling questions from there, but I haven't actually assigned anything from there for online homework. But I kind of want to get used to the format because I feel like that's the same format they're going to use for their online testing since it's already there and they already have the system made. So over the spring break, I'll assign a couple free response questions from AP Classroom, just so you can get a feel for how to submit your answers during the AP test this year. Okay. So thank you very much, and I'll see you tomorrow for Calc 2. Goodbye.